Welcome to the percentage yield lesson. So I'll say percentage yield, or sometimes I'll say percent yield, okay, but referring to the same thing. So what we're doing today is we're continuing with what we were doing the last few days where I will know some information about the reactants and we'll find out which one's the limiting reactant and then go through and calculate how much product should form. So when you're going about doing that, you're using a stoichiometric process to calculate out what should form, okay? So you're going to still continue to do those questions today. And when you calculate out, the mass of this substance was this, right? That's what's going to be considered to be the theoretical yield. So in a perfect world, if the experiment runs perfectly, there's no problems, you will get, this mass or this amount forming. But today, the new information I'm going to give you is, well, so that's the perfect world, but we're actually going to run it through a machine and analyze it, and stuff happens. Like when you're running a lab, stuff happens. You might spill some stuff you don't mean to, or you might lose a few crystals here. You might, lose a droplet there, or and so forth. So you've seen in some your labs that you've done that there's some problems that will happen that you try your best to be careful, but things happen so that it actually affects how much sample that's supposed to form. Okay, so you're going to be given information about here's the reaction, this is actually what you got. Okay, this is the mass that you were able to extract, where the theoretical yield will be, say, this is the mass that you should get in a perfect world, but in the real world, stuff happens, so this is the mass that you actually got instead. So today, when we get those two values, we'll talk about the issues here in a sec, but we're going to actually just calculate a percentage. So what you actually got versus what you should have got. So it's like a test. You got 75 on it, but there were 100 questions. So your percent yield is 75%. Okay, so it's kind of just calculating the percentage of something similar to the percent composition that we did already at this unit. So we're just going to take our actual yield, what we actually found by experiment, versus what we should have had, and then multiply by 100. Okay, so that's our goal. We're just going to discuss here, though, what happens. Like if we were being really, really careful and we were making sure we didn't lose any crystals, we didn't, spill anything and so forth, what issues can happen that we just can't control, okay? All right, so here are the four things: the nature of the experimental procedure, impurities, competing side reactions, okay? So the first one, nature of the experiment. You're not really looking at reversing reactions this year, but it's something that you will look at a lot next year because there's like this whole idea of equilibrium. So sometimes you'll produce stuff, you'll make this product, but actually it can also decompose and go back to the original, right? So it's like synthesis, but then you can get decomposition, right? So sometimes you'll have reactions where there's competing reverse reactions that will, again, like you try to create ammonia here, but then it breaks apart and goes back to the original substances. So you're not going to get as much stuff as you want that you should get theoretically if you calculate it out with stoichiometry. All right. So yeah, I guess I was saying that, in a perfect world, what are things you can control? There are some things like you try your best to, when you're running an experiment, to not lose any substance and so forth, but stuff still does happen. Okay, so it comes down to what kind of procedure, what kind of steps do you follow in order to create your product. Okay, so just yes, stuff happens even though you try to be really careful and try to have the best procedure. Okay, so yeah, you could lose small quantities of material. And sometimes you have to weigh it out, and so when you do that, you leave a bit of substance behind. Yeah, like they're talking about spilling and sometimes splattering and so forth. Okay, so like, again, try to be careful. Try not to have this be a huge part of your loss of material, but still stuff will happen. Okay, we also don't have like our equipment that we use in high school isn't great. When you go to university, it'll be better, but it's still we're still trying to improve on using better and better equipment. But again, we just need to develop better technology. So as we kind of go along and get better technology, we get better at getting our yields out. But yeah, there's always things that will affect how much product that you can form. Okay, there are other issues too where you are trying to create a certain compound, but maybe the stuff that you start off with, so it's out of your control, isn't completely pure. Okay, so there might be some residue, and it's not because the your friend beside you at the lab bench accidentally mixed the stuff together and caused a problem. It's more like if everyone was being careful, we still might have some samples that aren't pure, so that we can get some issues with when we run the reaction that we're not getting all the stuff out that we need, okay? And then, yeah, like we're just, so you can read through the stuff here. I'm just trying to give you some background information on just why we don't get 100% yield, okay? You're going to find as you go through and calculate stuff out um, that, yeah, like it's sometimes it's close, sometimes it's not as good. So again, I've had students in the past run an actual experiment where they go through and try to actually create a product, they extract it, and then they end up weighing it out. And the best percent yield that they could get was 2%. Okay, so out of the 100% that they were supposed to get, they did their best and can only achieve 2% yield. Okay, so um, yeah, so there's issues that can come into play, like impurities and so forth. Okay, if the material that you're using too is not fresh, if you can think of it that way, it's been sitting in the storeroom for a while, that can also affect how good of reaction that you'll get. All right, there are again, you might do this next year. If not, if you keep studying, going on into university and studying chemistry, you'll learn that there are substances where they look like they're the same, the chemical compound, right? Formulas are the same, but they're, if you look to see how the branches are attached, so there's cis platin and then trans platin. So basically, trans means like to go across. So these ammonia branches here are attached across, where these ones here are attached like kind of beside each other out of the four branches. Okay, so they are considered to be different substances, even though they chemically they are the exact same formula wise. Okay, and so what also happens in reactions is that you go through and you try to create a product, but like it's saying that the cisplatin, this is the one that's important for cancer treatment, but you're gonna, when you run a reaction, it forms both of these. You're not getting 100% yield of the one you need. You end up getting some of this one as well, okay, because it's considered to be a competing I guess reaction as well. So anyway, so just wanted to give you just a quick introduction to stuff that can happen when you run an experiment, and that's why it's like you won't get 100% yield, okay? But all we're doing today is we're going to go through, and again, in a perfect world, we should get this amount, but when we ran our experiment, we got this, so we're going to figure out what percentage, like how successful were we, okay? So let's go right to this page here. Okay, so we're going to look at this example here. So I'm just going to grab this formula, put it down here so we can write our information that we know about. Okay, so we're looking at arsenates are used in pesticides. Okay, are compounds of arsenic. So basically we have this ore of arsenic. If it's heated, it can decompose into iron 2 sulfide and into just the arsenic, okay? All right, so we know that we have a mass of the ore. That's going to be processed industrially, and then we found once we ran this reaction, we got 95.3 kilograms of arsenic. We need to calculate the percent yield of the arsenic, okay? So let's write down the information that we know. Okay, so we know the mass, and I'm going to call it the ore. We know the mass of this ore here. Okay, and it's 250 kilograms. Okay, and we know the another mass here, but it's what we have obtained. Okay, so that's actually the mass of arsenic. Okay, and it's the actual yield here, okay? So it's the actual mass. This is the actual mass. So we ran our experiment and this is what we actually found, okay? So we're not gonna write, it's the mass that we should find, okay? So that's what we, the mass that we always find when we calculate is the theoretical. Okay, and that's the one we need to actually find. Okay, so this is the theoretical mass or theoretical yield. Okay, so theoretical mass. Okay, but we also call these the actual yield and the theoretical yield. Okay, so we know how much was thrown into this reaction and at this plant, and then we need to know, go through what we did the last few days and go through, you know, go to moles, find the mole ratio, and then come back and find the mass. So that value that we were always calculating here was the theoretical mass. So in a perfect world, if everything was perfect with the reaction, this is the mass that we should get. Okay, but then we do have this information here about the actual mass that we did get when we ran the experiment, because stuff happens, and so then we have to at the end compare the two yields and find the percent yield here. Okay, all right, so I know a lot of you like using the graph stuff, so I haven't been doing this, so that's your given. This is what's required, and then our A is our plan, right? So here's our plan. We're going to go from the mass of the ore to the amount of the ore, and then we're going to do a mole ratio to figure out the amount of the arsenic, and then we're going to come back up and then find the actual mass of the arsenic. So that's the plan, and to get this plan working, remember we need to find the molar mass, or use the molar mass of the ore to find the amount of the ore. Then we need to do the mole ratio here using the balanced chemical equation, and then we need to use the molar mass of arsenic in order to get from amount of arsenic to the mass of arsenic. All right, so there's our plan. So we need the molar mass, so I'm going to go and find those. So I found the molar mass of the ore, okay, and so just reminder, this is the ore, and the molar mass of arsenic, which is what we need to find, okay, so we can kind of have them ready to go when we get to our calculations. All right, so I'm going to use the unit analysis method, okay, first, and then I'll show you the formula method. So we need to find the mass of arsenic, okay, and again, we are calculating the theoretical mass right now. Okay, and this is what we've been doing the last few days. It's always been in the theoretical mass. In a perfect world, this is the mass that you should get, okay? All right, so if you okay, so right now we need the mass of the ore, but if you see there, it is, it's in kilograms right now. So the mass of the ore is in kilograms, okay? So we've always been working in grams. Our molar mass is in grams, so we have to convert that to grams. So we're going to multiply it by 1,000. Okay, and then you end up with 4 zeros there. So that is now the mass that you're going to use so that you are in grams, okay? So again, just if you needed to remember what you were doing here, if you're studying it later, you multiply by 1,000 to get to grams, okay? All right, so that's the mass that you're going to use. You're going to use the mass that you know, and that's the mass of the ore. Oh, I just spelled gore. Okay, whatever. And then the first step here is to use the molar mass. So we're going to flip the molar mass and write, so this is the ore molar mass. Okay, so and then so the next step is the mole ratio. We're looking at our chemical reaction equation here, and again, when you don't see any coefficients like that, take a quick look and make sure it's balanced, okay? It is balanced, so we always put the one we don't know or we need to find at the top, so that's arsenic. And then the ore is 1 mole, okay? So it's a 1-to-1 ratio. And the last step here, the molar mass of arsenic. All right, and then do the quick check that you have everything in the right spot. Yeah, good, okay. And now calculate it out. All right, so then we end up with the mass of arsenic of this large value here, okay? And again, we're looking at an industrial process. A lot of product is being formed, so the numbers are a lot bigger than what we've been looking at in the last few days. Okay, so this is in grams. We need to remember, calculate the percent yield. So remember our actual mass up here is in kilograms. So let's put this back into kilograms. So I'm going to divide by 1,000. Okay, so I get it back to kilograms like that. And again, if you're looking at this later and wondering what happened there, so we just divided it by 1,000 to go back to kilograms. Okay, and so now we need to calculate out the percent yield now because we're not done yet, okay? So again, what you've been doing in the last few days, you went this far and then you would state the mass, okay? But this is the theoretical mass that you just found, okay? So this is in a perfect world, if the experiment went great, that's the mass that you should produce if you put in a 250 kilogram sample of the ore, okay? So again, you can interchange these, okay? The more specific term is the mass, because it is a mass we're looking at, but it is considered to be the theoretical yield, okay? All right, so let's calculate, the percent yield out now. Okay, so the percent yield of the arsenic, okay, is going to be, remember, it's the actual yield over the theoretical yield. Okay, and then multiply by 100. So let's fill that in. Okay, so the actual yield was given at the beginning of the question here. You know, we ran this process through this reaction, and then we actually obtained 95.3 kilograms. Right, and then, but we, theoretically, if it was perfect, a perfect experiment, you should have gotten this much of the sample. Okay, and then multiply by 100. Okay, so when you get to here, the questions that I'll give you, you know, the actual yield should be smaller than the theoretical because we're looking at, you know, something maybe, you know, you spilled some stuff or just something happened so that you end up with not as much as you wanted, okay? Yeah, so if your actual yield is bigger than your theoretical, go back and double check your work. Stuff does happen though, I guess, experimentally, where, yeah, you might end up with more stuff, actual yield than theoretical because maybe there are impurities or contaminations, so you end up producing something else. But just for when you're practicing now, though, just, you know, expect the actual to be smaller, okay? And if it's not, go and double check your work. All right, I'm getting 82.85, so I'm going to round that up to 9 because we're working in 3 digits here. So 82.9%. Okay, so Now make your final statement. So the percent yield is 82.9%. Oops. Let's say what it is. The percent yield of arsenic is 82.9%. All right. Okay, so not a lot of new stuff today. You're just doing what you did before the last couple days, and then you're just calculating out a percentage now, okay? Because you're given this new piece of information here where it's like, oh, well, this is what actually did get produced. So you just make a comparison with what should have been produced, what did get produced, and then you just report a percentage, okay? All right, I'm going to show the formula method now. If you want to jump to the example 2 in the video, you can do that if you just want to see the unit analysis method. Okay, so here's example 1 again. I'm just leaving all the given, the required, and the plan written out here, so we can just continue from the solve step. Again, so you're going to go through this box method here. It's still, you're going to go from mass to amount to the other amount and up to mass again, okay? So we're going to start off with finding the amount of the ore. Okay, in order to find the amount of the ore, you're going to take your mass and divide by your molar mass. Okay, so again, we're going to use the mass in grams. And then we're going to divide by the molar mass of the ore, which is 162.84 grams per mole. Okay, so you end up with a large amount of moles here. The first part of the box is done. Now we're going to do the mole ratio. So we're looking at comparing the ore to the arsenic sample. Okay, so if we look at the balanced chemical equation here, we're noticing that it's a 1-to-1 ratio. So the nice thing is then, okay, so then the arsenic has the same amount of moles. Okay, all right, so that step's done. Now we just have to get to the mass of arsenic. So we're going to do that by taking the amount and multiplying by the molar mass of arsenic. Okay, molar mass is 74.92 for arsenic. Okay, so then we get to a really large mass value here. Okay, and then we want to divide by 1,000 so that we're working back in kilograms again. Okay, and then we're going to do the percent yield over here. Okay, so the percent yield we're taking our actual divided by our theoretical and multiplying by 100%. Okay, so your actual was given at the beginning of the question, so this is what was obtained from the experiment, but theoretically you should have made this much of the sample. Okay, it was a perfect world, everything ran perfectly, we had the best equipment, this is what you should get, and then we got 82.9, yeah, 9%, okay? All right, and again, don't forget your final statement and the keyword, okay? So I'm okay if you write percentage yield or percent yield. Just make sure, write the key statement though, okay? Percentage yield of arsenic is 82.9%, like that. Okay, all right, let's move on to another example. But again, if that one example was good enough, go ahead and start the practice questions and then try the checkpoint, okay? And then you're done. It's unit number 4. Good job. All right, let's move to example 2 here. So just read through it and do the usual find information that's given to you, and then yeah, and then go through and find the percentage yield. Okay, so we have methanol. You can create methanol with a reaction of carbon dioxide and hydrogen. Right, so we have some information about, we know the mass. Okay, so we know mass of hydrogen, 20 grams, and is reacted with an excess of carbon dioxide. Excess. Okay, and then we are trying to find the mass of methanol produced. Okay, and we know the actual, so we'll call it actual methanol that was produced was 102.0 grams. Okay, so again, this is the methanol. That's the actual methanol, but then we are looking at finding the theoretical. Okay, all right, so what's different about this one compared to the last one is you're going through this investigation and it's telling you that 20 grams of the hydrogen was reacted with an excess amount of carbon dioxide. So in a way, this is like literally telling you, because you know when you have two substances, we need to figure out which one's limiting. It's telling you that this is an excess. So right away, that's the excess reagent, and therefore this is the limiting reagent, okay? So just kind of look for questions like that where it'll tell you literally which one's the limiting reagent. But if you were given this problem and it said, oh, I used a mass of this and a mass of that one, you don't know which one the limiting is, so you have to do that step, okay? All right, but today it's about percent yield, so let's just keep it simple and just do that. All right, so we know that's limiting, so we don't need to do the limiting reagent step. All right, so here's our given information, I guess. Here, I can put it here. This was given to us. This is what's required, the theoretical yield. All right, here's our plan. Okay, so we know the mass of hydrogen. We want to go to the amount of hydrogen, and then we want to find the amount of methanol so that we can get to the mass, the actual theoretical mass of methanol. Okay, so again, when you are working through these stoichiometry steps, you are just finding the theoretical amounts and masses that you should get in a perfect world, okay? All right, and then here's our plan again. Remember to jump around to these different parts of the box. I don't know, I guess you can think of it as islands too. You need to be using the molar mass of hydrogen here, you need the mole ratio here, and then the molar mass of methanol. So let's calculate the molar masses out. So there's the molar mass of hydrogen, there's the molar mass of methanol, so it's there when we need it. We are gonna, again, start with the unit analysis method. Okay, so again, we are finding the theoretical. This whole process here is finding the theoretical yield, okay? All right, so what is it that we need to find? We need to find the mass of methanol. Okay, so in order to do that, we need to find what's given to us, and that is the mass of the limiting reagent here of hydrogen. All right, so we need to go from mass to amount. So we're going to divide by the molar mass. Okay, and then now we're at the mole ratio step here. So we're looking at the balanced chemical equation back up here. We have hydrogen to methanol is 3:1. So the one we know goes to the bottom. The one we need to find goes to the top here. And that way the units will cancel out appropriately. All right, and the last step is to use the molar mass, which is 32.05. Okay, all of the units cancel out nicely, so let's calculate this out. Okay, and we end up with a mass of 105, 77. And again, remember, this isn't our final answer in this question, so that's why I'm carrying some extra digits here. Okay, so we found the mass of methanol. Here it is. And again, just a reminder, this is your theoretical mass. Okay, so today what we're doing is we're finding the percentage yield of this reaction. Okay, so again, it's not telling you specifically what it is, like the percentage yield to what, but if you're like kind of going through and analyzing it, we're talking about methanol here, so that's what we need to find. Okay. All right, so let's go and do that. So percent yield. Of methanol. Okay, so remember we have actual over theoretical times 100. Okay, so the actual amount was 102 grams. Okay, remember, a reminder that, remember, it doesn't matter what units you use here for the yield, as long as they are the same units, okay? So if it's grams and grams, kilograms, kilograms, moles, moles, those are all okay. All right, and then this reaction is pretty good because we have a 96.4, we need 4 digits, sorry, 3. Okay, so I'm just double checking. Yeah, I have 4 digits here. Oh, I have 3 digits. Okay, so here's one where I have 3 digits here, 4 digits here. We want to go with the one with the fewest number of digits. So yeah, we're back to just 3. Okay, all right. So make a therefore statement. Therefore, the percent yield of methanol is 96.4%. Okay, so that would be, I would think, pretty successful because we only lost about 4%. Okay, all right, so I'm just gonna do the same one here now with the formula method, okay? Again, I just copied out our given, required, and our plan step, okay? So we'll just start from the solving step here. So again, in our box here, it says we have to take our mass of hydrogen and we need to find the amount of hydrogen. Okay, in order to do that, we need to take the mass and divide the molar mass. Okay, so we have 20 gram sample here, dividing it by our molar mass of hydrogen. Okay, and then we end up with an amount of 9.90099, okay, moles. All right, so that first part of the box is done. Now we need to do the mole ratio. So we're going to look at, okay, we know hydrogen, and we need to compare with the coefficients in the balanced chemical equation for methanol. So it's a 3:1 ratio. Okay, so since it's 3:1, so to get to methanol, we got to divide by 3. Okay, so if we have this 9.90099 moles of hydrogen, we're going to divide that by 3 to find the amount of methanol. Okay, so there's our amount of methanol. All right, okay, that's the mole ratio step. Now the last step, let's get it to mass. We need to multiply by the molar mass. Okay, so amount times molar mass. And that is 32.05. So we end up with a mass of 105.7756 grams, okay? All right, not done yet though. We are finding the percent yield now. Okay, so we're going to take our actual over our theoretical, multiply by 100. Okay, so the actual yield was 102 grams. That was given at the beginning, saying we ran the reaction, this is what we obtained. But theoretically, in a perfect world, this is what we should have just obtained from the reaction here. So take it, divide it out, and don't forget to multiply by 100. There's your percent yield. Okay, don't forget the key word, okay? The percentage yield of methanol is 96.4%. Okay, all right. So I know there was a lot of work there, but hopefully you can see that it was just the same old stuff, just a little new piece on the end of it, okay? All right, please go practice these and try the checkpoint.